So now we're ready to talk about Newton's third law, and this is the third out of the three of Newton's laws of motion. So the third law is the one that it's a little bit easier to remember probably. For every action there is an equal and opposite reaction. So if object A exerts a force on B, then B exerts a force of negative F on A. So, if we have an object and let's say we push on this object, we're going to feel an equal and opposite push on us every time, even if the object starts to move. Because even as we push something and it's moving, we still feel a force backwards on us. So there are a lot of examples of Newton's third law in everyday life, and one of them you can see here with the car tire. The car tire pushes backwards on the ground with a certain amount of force, and then the equal and opposite reaction is the force of the ground on the car tire in the opposite direction, propelling it forward. We already talked about someone pushing something. As we walk even, our foot on the ground, we push backwards, and the equal and opposite reaction is a forward push on us. And so we see this all over the place. We've already defined a little bit of what mass and weight are, but it's very important to distinguish between the two. Mass is inertia. It's the resistance to an acceleration. The more mass you have, the more resistant it is to acceleration. Now weight can be defined as the force due to gravitational attraction. So how much pull we get from a force, and so weight is a force, and that is dependent upon the actual planet or location where we have that. And so the way we calculate the force of gravity, or weight, capital W, is mg. G we're going to remain as just as plain 9.8 meters per second squared, not negative 9.8, not negative g. The only time you use negative g is in free fall. If an object's in free fall and you're using one of the constant acceleration equations. So why don't you go ahead and try to calculate this person's mass. The mass is 68 kilograms, and go ahead and calculate their weight in newtons. So go ahead and pause the clip and you can try that. Okay, so you should have gotten 666.4 newtons as the weight of the person, and the weight again is dependent upon the acceleration due to gravity here on Earth, as compared to maybe a different location. So what we're going to do next is, what is the person's weight on the moon? The acceleration on the moon is 1.6 meters per second squared. So go ahead and try that, and then we'll compare that to the weight of this person on Earth. Okay, so the way we would do that is, again, F equals ma. We have the mass 68 kilograms, and 1.6 meters per second squared is the acceleration on the moon. So 68 times 1.6, 108.8 newtons would be the person's weight on the moon. So the normal force, the word normal means perpendicular. So that force, if you have an object that's resting on the surface, you have the force of gravity. The normal force is perpendicular to the surface, and it's always perpendicular to whatever surface that you have, and it completely cancels out any forces that are perpendicular to the surface. So in this case, force of gravity. As we work through second law problems, it's important to have a game plan as we work through these. So the first thing that we're going to want to do is draw a free body diagram. And we've already done quite a few of those so far. Next, you want to set up a coordinate axis. So, what's the positive x, negative x, positive y, negative y. Then you're going to set up the second law equations with the forces in the x and y. And it's important to do these separately. So some of the forces in the x, some of the forces in the y. And then we can identify the numerical data that fits it. And then we can substitute the numbers into those equations and then solve them. So we're going to go ahead and apply this to a situation where we can take a look at the normal force, look at the force of gravity, and evaluate it. So let's say we rest an empty glass on a table. So first, go ahead and draw the free body diagram, identify how many forces are acting, and then determine if these forces are equal and opposite. So you can go ahead and pause the clip and then start when you're ready. Okay, so if we look at our forces, force of gravity, normal force, and we only have those two. So there's two forces acting. We identified these forces, and they are equal and opposite. So the normal force completely cancels out the force of gravity. The net force is 0. Now, let's say we have this glass, and we're pushing down on the glass, and the glass's mass is 0.27 kilograms. We press down with 2.5 newtons of force. So go ahead and draw the free body diagram, determine how many forces there are, and then we're also going to go ahead and calculate what the normal force is. But go ahead and draw the free body diagram first, and then when you're ready, you can start the clip again. Okay, so we have the force of gravity. In this case, there's a force applied downward, and then we have a normal force that if we added up the two downward forces, they would equal the upward force. And so, and that upward force would be the normal force. So now what we're going to do is determine what the normal force is. So if we set up the sum of the forces in the y equals ma into y, we have the positive normal force plus the negative force of gravity plus the negative force applied. And remember, acceleration is the change in velocity. There's no change in velocity. So that comes out to be 0. And we know what the force applied is, mg for acceleration due to gravity, negative 2.5 newtons. So go ahead and pause the clip and see if you can determine the normal force. Okay, so we should get for the normal force 5.146 newtons. A common error here is to forget that it's mass times 9.8. So it's the mass in kilograms times 9.8 to get the force of gravity. And then we can determine the normal force from there. Okay, so now we're going to take a look at what would happen if we pulled up on an object. And we had a mass of a 100 kilogram object, and we want to find the normal force. So we first want to draw the free body diagram. We have the same force of gravity here, and then we're pulling up on it. Therefore, if we're pulling up on it, the normal force isn't as much. And that's what we want to determine here, is what is the normal force. And so, yeah, go ahead and set this up like the last one, and see if you can determine what the normal force is. You're going to want to write it out in variable form first. Okay, so let's see how you did there. We've got the positive normal force plus the negative force of gravity plus the positive force applied, and we should get 977 newtons as our normal force. And so as we work through this, it's important again to remember when we multiply the mass times 9.8, the force of gravity there, and then we've got our force applied that is counteracting some of that, not a whole lot. If you can see there, it's only contributing to a very little bit amount of that upward force, so it's mostly still the normal force. Okay, next we're going to take a look at a situation where we have three boxes, and we want to determine the how much force is felt between these two boxes and how much force is felt between these two boxes. And we know that overall force is this, and what we're going to do is try to figure out what's happening, how much does it feel here and how much does it feel here. And so the very first step, what we're going to do is we're going to treat this whole thing as one object. 1, 2, and 3. So the masses of all of those we're going to consider as one, and then the force on this is just that 7.5. So if that's true, if this whole thing is treated as one thing, we can determine what the acceleration of the system is, and then we can break it down from there. Okay, so now that we have the setup here with the free body diagram, we've got the normal force, we've got the force gravity, we have the force applied, and we're treating this all as one object, we can determine the acceleration. So we know that the normal force, force gravity are balanced, and for the acceleration of the whole system is negative 0.798, and so that's the acceleration of the entire system. Now that we have the acceleration of the entire system, we can break it down into the individual parts to determine what's going on. So what we can do is we know that box 1 and box 2 are there, and we can treat that as a system, and we can figure out what's the force right here in between them. We know that box 1 and box 2 are accelerating at the same rate as the whole system, so we can figure out how much force is felt there, and so that's the force that this would feel in between as we break it into that part. And then for the last part, we want to find out what's the force right here, how much force is felt, and we know that the last box is 1.3 kilograms. It's also accelerating this much, so we can determine how much force it's taking to make that happen. So negative 1.04 newtons would be what it feels there.